All right, lesson 1-6. Today we're going to look at function operations and composition of functions. Before we get started, let me walk you through how to get to where we are. I'm in Power School Learning, or I'm in Clever rather. I'm going to hit the Power School Learning button. After you choose the class, pre-calculus, I want you to go to chapter 1 folder, because this is lesson 1-6. That means chapter 1. So I'm going to go to chapter 1 and scroll down until I see 1-6. It will be near the bottom. There's only one more lesson in chapter 1. So it's almost test time. Yeah.
No.
Yeah, it is. So it is a 9-6 weeks, but we'll still take tests at the end of each unit. So we're at lesson 1-6 here. What I want you to do is at the bottom, this is just kind of going over what you're responsible for each day. Number 1 is just to show up. There's Zoom links, all that. There's digital resources in case you're absent, in case you lose your packets, in case you want more help, whatever. Those are all there. Make sure you take your attendance. We're pretty good in this class. Number 3, here's where we are right now. Number 3 is what we do during class. It's the packets. We can turn in our packets as we go. I would suggest you open up, it says to click this exam link that's talking about right there. Open that up. Later after class, you'll have homework for this assignment, which will be due Thursday. And for you guys, since B-Day hasn't had this lesson, this Friday, you'll not have this coming Thursday, but it'll be the Thursday after. So you'll have almost 2 full weeks to do this lesson. Lesson 6, I'd encourage you to open that up and you can type in your answers as you go. So I have it open here. You can type in your answers as we go. So number 1 here, I know it's not on the lesson exam, but I'm still going to go over it. There are, count them up. How many transformations? I hear 3 very frequently. And I understand why it's 3. It's actually 4. There's one that's hidden in there. There's a 4th. The 4th is the negative symbol. Most people don't realize that negative itself is a transformation. So let's just name the transformations, not the direction or anything like that. What happens when you turn a graph negative? It flips. It reflects. That's a reflection. So we'll talk about the type of reflection in a second, but that's a reflection. Okay. What about when you multiply a number by 3? How does it change? It gets bigger. It's a stretch if it's telling us the truth. We'll note if it's telling us the truth in a moment. What happens if you add or subtract a number? It shifts or slides or translates. That's the idea. It's going to shift it some way. So those are our 4 transformations. So now we're going to go in order from left to right. This reflection, this negative there, is that inside of F's equation or is it outside of F's function? Outside. So if it's outside, according to Hyvo, rule 1, outside is vertical, meaning it's a reflection of Y values. All positive Y values would become negative. All negative Y values would become positive. Now, here's what's tricky. Whenever you reflect Y values, so check this out. I'm just going to use this point. If I reflected that point, it becomes 0, -3. Okay. You don't have to write this down in your packet. I'm just showing you. It would reflect down and become 0, -3. Which axis do you actually cross over on your way to reflecting that point? You go over the X. Here's what's tricky is on the test, it's going to say reflection across the X-axis. Across the X-axis. Why people choose to test that way, I don't know, but that's the way it's going to be. And it's tricky because it's a vertical reflection, but it's not crossing the Y, it's crossing the X-axis, which a lot of students select that wrong. So just be aware. It reflects across the X-axis. Okay, I'm going to take this off now. Second one, that 3, is that inside or outside? Outside. Does outside, meaning vertical, lie or tell us the truth? Tells us the truth. So this would be a vertical stretch by factor of 3. Vertical stretch by factor of 3, which means every Y value gets multiplied by 3. Vertical stretch by factor of 3. So if you had a table, all Y's would get multiplied by 3. Okay, our next transformation. This -2, is that inside or outside? Inside, so it's going to affect the X's, the horizontal. It's going to lie or tell us the truth. It's a lie. So it's not going to go to -2. It's actually going to go to +2. It's going to go right 2 units. Slide right 2 units. Should say that. Be more accurate. Slide right 2 units. And then finally, I have a +2 on the outside. plus 4. I'm sorry, plus 4 on the outside. Is that vertical or horizontal? If it's on the outside, it is vertical, which means up or down. Do our Y's lie to us or tell us the truth? Tells us the truth. Our Y's tell us the truth. That's why we marry them. So this will go up 4 units, slide up 4 units, I should say. Slide up 4 units. And so that would be our 4 transformations there, written out in English. All right, number 2. We're going to change this graph now to accommodate this problem here. It says we want to have f of x plus 1 minus 1. So I want you to think inside about this plus 1 that's inside right there. If it's inside, is that horizontal or vertical?
Horizontal.
It's horizontal. It's inside with the x, so it's going to change x's. Does it lie or tell us the truth? Lie. So it's not going to add 1 to every single x. It's actually going to subtract 1 or go left 1. So this will be a slide left. Slide left. So each point that's on this graph will get moved over 1 point or 1 direction left. So each one will get moved over 1 left. Each of these points that are there. So I moved my points over 1 left. Now, before you do it, unless you like erasing, what's that minus 1 going to do? Why is it going to go down 1? Outside's vertical, and vertical tells the truth. So that'd be slide down 1 unit. So all of these go now down 1 unit. I kind of run out of space down there. And it's not really letting me go down further, sorry. But these would be my locations of the points. So if I were a good artist, I would do this really fast, but I'm a terrible artist, so I'll go slow and still probably miss my points. But it should look something like this. There would be our answer. And if you wanted to label your points to help you out, we went left 1, down 1. So this would become, oh, I didn't realize these were counting by 2s. My bad. But this point should be, these were not counting by 1s. So this should be a -1, comma 2. That's what you'd be looking for on your lesson exam. So if you have this open, you can go through and try to find the correct solution. You're looking for -1, comma 2 to be the correct point. So you just find wherever, there it is. This one would be shifted down 1, left 1. Okay, finally, remind me, what do these vertical bars mean when you see that around f of x?
Absolute value.
Absolute value. What does absolute value do? Flips what?
It flips the x's.
Turns the number positive. It's how we calculate distance in math. It's for distance is what it's used for. It turns negatives positive if it's telling the truth. So will this be telling the truth or lying? It's telling the truth. Why is it telling the truth? Because it's on the outside. So it's going to take our y values and turn them to the truth. So I'll do this one in red. It's going to take any y value and turn them positive. That's negative. So for example, this point right here, 2, comma -1 would become 2, comma +1. So instead of at this point going through and becoming negative, this graph would come up this way and go there. And over here, the same concept applies. Instead of being -2, -1, it would become -2, +1. So like this point right there, -2, +1. And so this graph would just kind of hit this way, and it looks like it just kind of continues on that path. So it would just continue on this way like that. All this other graph, the orange would be gone. So the orange was for number 2. So I could get rid of that orange now. All that's gone. But anywhere it fails the vertical line test, what do? Do I get rid of the new or get rid of the old when it fails the vertical line test? Old. So you'd be looking for the picture that looks somewhat similar to that. That's what you would be looking for number 3. So if you pulled that up, number 3, you would need to find which picture would represent what we just had there. Which it looks like to me, it's that one right there. Okay, before we start new stuff, I do want to remind you, What would you do differently if you had the absolute value with on the x? What if the absolute value was inside on the x? So all positive x's become negative x's because it's a lie. And so instead of this one, what I'm going to do here is I'm not going to draw it on its own. I'm just going to do it here. It takes the positive x's. And so this point is at 2 to the right and 1 down. It takes a positive x and makes it a negative x. 2 to the right, 1 down, this point here. So starting here, -2, comma, -1. This would reflect and be the same because it's like a parabola. But starting here, it would make it, it'll go that direction, and this would be gone because it's the old. And it fails vertical line test. So you'd look like a sombrero. That's what it would look like if you had the absolute value of x. So it would look like a sombrero. All right. New stuff. 1.6. Lesson 1.6, all about combining multiple equations together. So let's talk about putting some equations together. I know you don't have this slide right here, but basically what it's saying is you will see these symbols, f plus g of x, and all it means is you take your f equation and add it to g's equation. F minus g just means you subtract. Multiply means multiply, divide means divide. And remember, for our domain, you're not allowed to divide by 0, so we will need to solve for domain as we go along today. I will write this as we go, but this is a basic sheet just saying when you have 2 equations, you can do the normal math with those 2 equations. So let's see 4 examples I have for you. Example 1, A, B, C, and D. We'll start with f plus g. It says, given these 3 equations, f, g, and h, find the function domain for f plus g. So what we're going to focus on in this first problem, example 1a, is only f plus g. So here's what I want you to write. I'm going to write shorthand, just f plus g like this. You can, if you want, put the parentheses around it of x. I'm not going to do that. I'm just going to be shorthand today and say f plus g, because you get to calculus, and that's the only way your calculus teachers will write it. I shouldn't say that. It's not like I've had every calculus teacher in the planet, but I know that's how most of them will write it, f plus g. And what you do is you take your f equation, this f equation up here, and you're going to take the equation. I'll make it x squared minus 2x. And what we will do is add that to g's equation. G I'll do in green, which happens to be 3x minus 4. Now, here's the deal. When you do this, what we are doing is substituting. I am substituting instead of the letter f, I'm substituting f's equation. When you substitute, if mathematically you want to get these right 100% of the time, be consistent, always substitute with parentheses. It will matter, not on this problem, but it will matter on part B, it'll matter on part C, it won't matter on D, but it will on B and C. So if you just want to be right all the time, whenever you substitute, use parentheses. So I've substituted f's equation in here. This was f, if you want to note that. This was g. We are supposed to add them. So first question, can we remove the parentheses at this time? Parentheses mean multiply. Is there anything for this front parenthesis to multiply with or to distribute through? No. So I can get rid of the front one, x squared minus 2x. What about the back? When I distribute the plus through, does a plus change anything? No. This is still a positive 3x. And what is a plus of a negative? Still negative. So that's what I have. You'll see on the next problem what happens when you distribute a negative. It'll change the problem. So now I go to combine my like terms. I see right here, I have like terms. When you add and subtract, you only combine like terms. It's kind of like you saying, hey, I have 1 apple, I have -2 oranges, I have +3 oranges, and -4 bananas. You only deal with the ones that are alike when you add and subtract. These here. So when I combine my like terms, I owe somebody 2 apples, but I have 2 apples or 3 apples. How many apples do I have if I settle my debts? Just have 1. And so this would be f plus g. Again, if you wanted to write f plus g and put parentheses around it of x, you can. That's, I guess, perfect form. But shorthand, you just write f plus g. Okay. Now, with domain, On lesson 1.1 and lesson 1.2, I spent extensive time with domain. I told you first, when you're dealing with equations, we assume the domain is all reals. That's what we're supposed to, most graphs begin as all reals. There are some rules though that'll impede it from being all reals. Number one is division. What can we not divide by? We cannot divide by 0. That's one thing. There's another thing you cannot do. Cannot take a negative square root. Cannot square root a negative number. Okay, so, and 3 is coming. So to be determined. That has to do with logarithms. When you look at this problem, do you see any division? No, so division doesn't matter on this problem. Do you see any square roots? So not a square, but a square root. No, so that means it's going to be all reals. The domain here is all reals. That's our domain. All right, I'm going to copy these rules because I'm going to be using this throughout the day. So I'm going to copy those so I can paste them later. All right, let's now look at part B. Example 1B says, same problem, same setup, only one thing's different. It says, let's find f minus h. Notice it says f minus h. Does not say f plus g like the previous. This one says f minus h. So what I'm going to do here is take my f and subtract h's equation. Again, I'm writing shorthand. So I will use parentheses. The parentheses are f's equation. F's equation is x squared minus 2x. That is f. Now we are supposed to subtract h's equation. I'm sorry, h equation. So this time I'm doing h, which is negative 2x squared plus 1. There's my equation for h. Now here's why using parentheses really matters. Nothing occurs on the front parentheses, so I can get rid of that. I don't need it. I can rewrite that as just x squared minus 2x, x squared minus 2x. But over here, I'm subtracting this whole parentheses, which means I need to distribute that negative through. So a negative of a negative 2x squared becomes positive 2x squared, and then a negative of a plus 1 becomes a negative 1. So that's why you need to use parentheses, because oftentimes we'll be distributing or something like that, and it'll make a difference if you don't write the parentheses. This 1 would have been a positive 1, not a negative like it's supposed to be. So now from here, I combine my like terms. I have a positive x squared and another 2x squareds. How many x squareds is that? That is 3x squareds, which means I have a minus 2x and a minus 1. That is f minus h. Again, if you want to write the full way, you would say f minus h, parentheses, and then of parentheses x. That would be my solution there. So looking at those domain rules, sorry, hang on a second. Let me try this again. Copy, paste. Okay, looking at those domain rules, do you see any division? Is there any divisions?
No.
Nope. Okay, what about square roots? No. So guess what? Domain is all reals. Which also you could write as negative infinity to positive infinity. Let me go ahead and put that on the previous problem as well. You could write that as negative infinity to positive infinity. All right. Let's look at part C. Part C says, given the same problem, to find f, and this is a really big multiplication symbol. It wants f times g. Just to make it clear in your notes, if you want, you could write it with an x and say f x g. What we're looking at is f times g, or I guess you could just make it a smaller dot. I guess that would work as well. Just f times g. F times g means you're going to take the equation f x squared minus 2x. And you're going to multiply that times g's equation, which is 3x minus 4. To do this correctly, I want you to remember that old algebra technique of foiling. If you're like, what is that? Well, let me show you. Foil. Oh, you can do box method. That works too. Box method is fine. I'll do FOIL most often in this class. It's where when you're multiplying two groups together, you need to fully distribute. So the x squared is going to get multiplied times the 3x. This is what the F, which actually stands for first times first. I'll just write first. First times first. What is x squared times 3x? If you're not sure, when you multiply coefficients. 1 times 3 is 3. If you have a common variable, which we do, it's x. You add powers. So 2 plus a power of 1. What's 2 plus 1? 3. So that'd be 3x cubed. Next, you do the O, which stands for outside times outside. So 1x squared times negative 4. This is outside times outside. So I'll just write outsides. So 1x squared times negative 4. 1 times negative 4 is negative 4. That doesn't have an x, so this one just stays the same, x squared. All right, next step over here, we have the I, inside times inside. So I'll write down insides. Negative 2x times 3x to the first. So negative 2x. So negative 2 times 3 is negative 6. This is x to the first. This is x to the first. 1 plus 1 is 2. And finally, last one, negative 2x times negative 4. This is what you call last. This is the L. Last times last. Negative 2 times negative 4 is positive 8. And there, that doesn't have an x, so I just have x to the first power. When I combine my like terms, we'll have our answer. I can combine those. So F times G of x would equal 3x cubed. That's minus 4x squared and minus 6x squared. If you think of money, it's like saying I owe $4, I owe someone else $6. How much do I owe total? I owe 10. I owe more negative, so I owed 4, I owed 6, I owe 10 plus 8x, and that's my equation. Did we do any did we do any divisions of x's? We did not do any divisions of x's. Did we have any square roots in there? Domain's all reals. From negative infinity to positive infinity. All right, and one more before I give you one. Part D, it says find h divided by f. H divided by f here. So I'm just going to say h slash f equal h. Again, I would substitute into parentheses, although on this one it won't end up mattering, but I will still do so. Negative 2x squared plus 1. And the f was x squared minus 2x. This g over here? Okay. That's just an extra. I'm not using it on this problem. But all the problems we've been given all three equations. Okay, quick question for you. Remind me, we talked about this one of the days earlier. Can I cancel just the x squared and the x squared? Can I cancel a term, or can I only cancel if the factors match? Only the factors match. This one won't be able to simplify. There's nothing to simplify there. So if you want to rewrite your answer, you could just rewrite it again. I'll show you perfect form would be h divided by f of x equals, and then you could take away the parentheses since nothing's simplified. Negative 2x squared plus 1 over x squared minus 2. That's going to be our minus 2x. Sorry, that's going to be our answer here. But it can't be too easy for us. Is this domain going to be all reals this time? No, why not? Can't divide by 0. This time we had this division. So to solve for our domain, I should have put that a little bit higher, but too late now. I'm just going to clear a little bit more white space so you can have a number line as well. The domain here, I'm going to do a number line and say, okay, we know we cannot divide by 0. So on a number line, what that means is the graph, though it won't hit 0, it'll hit every positive and negative number. So what I'm going to do right now is draw a circle around 0 and draw an arrow going right and an arrow going left. And we're going to see what value is that actual break going to be at. Would it be at 0 or somewhere else? So you take your denominator and you say the denominator x squared minus 2x cannot equal 0, because that's what we're not allowed to do. We're not allowed to divide by 0. Okay, so I'm not dividing by 0. Now, to solve this, if you have a power greater than 1, you need a factor. This problem, luckily for us, has the easiest factoring. What do you do when there's something in common? What's shared here? X. We can do what's called the GCF, greatest common factor. If I pull out the shared x, if I pull out 1 power of x, I'm left with x minus 2. And now to solve, I'm going to use the algebra 2 zero product property. You're like, what is a zero product property? Well, you learned in algebra that if you're multiplying, there's only one way to ever get a 0. There's only one number you can multiply by and get 0. Think about it. 5 times 1 is not 0. 5 times 2 is not 0. 5 times negative 1 is not 0. 5 times negative 5 is not 0. 5 times 1/5 is not 0. 5 times what number gives you 0? 0. Only 0. So what you learn in algebra is if you're in this setup where you're multiplying and getting 0, or in this case, not getting 0, you can set each one individually as not being equal 0. Either x is not equal 0 or x minus 2 is not equal to 0. So we're actually going to have 2 answers. We have this one already. That one's done. X cannot equal 0. Over here, I would need to do one step to isolate this x. What's the opposite of subtracting 2? Add 2. So we'd find out x also cannot equal positive 2. X cannot equal 0. It also cannot equal positive 2. So if I wanted to add that on the number line, there'll be another little gap here. We'd say it cannot equal the number 2 either. Okay, great question. So you could say like this. You could say the domain is x cannot equal 0 or 2, but x is all other reals. You actually wouldn't have to throw in that part. I'm doing it. It's all reals but 0 and 2. Just want to make sure you understand that. It's all reals except for 0 and 2. You could also say, using the number line, it'll go left to negative infinity. And it'll go all the way right until 0, and there'll be a break. So that's where you do union. It exists between 0 and 2. So I do 0 to 2 and another union, and then 2 to positive infinity. You could write it that way. As you write your answer, I will show you the graph, and you'll see that this domain is right. So f of x is x squared minus 2x. H of x was negative 2x squared plus 1. We were looking for h of x divided by, I don't know if it'll let me do it the same way. Let me try it. H divided by f of x. Let's see if it works that way. It doesn't. You have to do it each individual. H of x divided by f of x. Let me take off this x. That's not working. Let me try g. Oh, that was going to work. I just need to turn off these two. Sorry. Let me do this one more time. H of x divided by f of x. Okay, when you look at this graph, What can you tell me about how far left does this graph travel? Forever. How far right does it travel? Forever. If you smash this like a garbage truck, crash compacted it, would every spot in the middle be filled in, or would there be a small little break? A small little break. And I messed up somewhere in this equation. What did I type in wrong? Oh, X. There we go. There would be a small little break, and the small little break would be between these two pieces at 0 and these two pieces at 2. If I convert this to a table, you'll see it's undefined at 0 and undefined at 2, just like we said. So it does work. Okay, I've done a lot. It's time for you to try some. DOL number 1. Try this problem, see what you come up with. All right, so now we're going to move into what this lesson is really all about, where it kind of gets new. It's called composition of functions. So some of you may have been introduced to this when you were in Algebra 2, but we're going to hit it a lot more in depth, especially as it pertains to domain and range. And so here's what's going to happen is we're going to have a function, and I've got an illustration for what all this means. But what we're going to do is we're going to substitute one entire function into a second function. So when you see f of g, what it actually means is instead of having f of x, you will substitute the entire equation of g into f anywhere you see an x value. So let me show you this way. What's happening is this. If you had f of x, let me try this again. If you had f of x, and you had some equation g of x, what we do with function composition is this. We come in and we say we're going to substitute into f's equation. We'll remove whatever the x was, and anywhere we had an x in f's equation, we'll replace it with g's entire equation. That's what's happening. So when you substitute, I want to remind you, because this is where a common misunderstanding is. When you substitute, the entire original value comes out and it's replaced by the new value, which that's not really cooperating with me anymore. But you would substitute in the whole piece here. Let me see if I can backspace it to get back to where I wanted it to be. You would take the whole equation in there. So said this way, think of an illustration. One I used last year when we were around this time is Dak Prescott's playing football for the Cowboys. He's running out, gets tackled, and his leg breaks. The Cowboys have to do a substitution. Does that mean Dak Prescott stays in the game and keeps playing with another player on the field? No. What happened to Dak Prescott? He gets taken out and someone else goes in his place. That's the idea. We're going to always remove an x and replace it with something else. So you're not going to add one x on top of another x. That's where students mess up this, is they try to substitute and leave the remaining. It's like they try to leave Dak Prescott and put in another quarterback. But you got to take out one to replace the other. So I'm going to get down here and show you what this means after I work a problem or two. Then we're going to come back and I'll explain what this means. Because right now I'm guessing you have no clue what this is trying to illustrate. So let me give you the first problem. It says let's compose two functions, f and g here. Let's find f of g of x. Honestly, what that means is this. F O G of x. What that honestly means is this. F parentheses g parentheses x, close parentheses, close parentheses. That's what it means. You're substituting in math language, you are substituting the g's equation into the f's equation. I think it's easier to illustrate this way though. I'm going to stack my equations. I'm going to first write f, 2x squared minus 1, and underneath it, I'm going to write the g equation. I'm going left to right. So I did f first, now I'm going to write g's equation. G's equation is x plus 3. Now, if you had a number, we would write the number there. This one, they just give me an x. So I'm not too worried about that. You could put an x. But ultimately, what happens is you're going to substitute in to the equation above. So you would just substitute in. Since this is an x, it's not going to change the first equation. I would substitute an x in, but I already have an x. It's not going to change anything. So I'm just going to skip that and only write down the f and the g. From here, I take the g's equation and I substitute it in for the x. Now, remember what I told you about substitution. Will this x stay there? No, this x right here is going to come out, and it's going to be replaced by x plus 3. So I will have 2 times parentheses x plus 3, close that parentheses, squared minus 1. That right there is the composition of f of g. So you could write f o g of x, if you wanted to write it out perfectly, equals 2 times x plus 3 squared minus 1. That would be the solution right there. So the stacking technique, that's what I call this stack, just helps me substitute in correctly, just helps me see where everything's going. That would be my equation. I could ask the domain rules. Instead of writing all those down, I'm just going to ask you, do you see any divisions here? Do you see any square roots? No, so my domain would be all reals. You could write it that way, or negative infinity, comma, positive infinity. That domain would be all reals. Part B. We're now going to find g of f. And so if I were you, let me first write exactly in math language what this means. G of f of x. In math language, what that means is, instead of having the domain on g of x, you're going to replace the domain of g with the range of f. That's ultimately what's happening. Now that's the math language. To write it out by symbols, I take the first letter, which is g, and I'm going to write out that equation, x plus 3. And I'm going to stack it on top of the next letter, which is f. 2x squared minus 1. And by the way, if there were more letters and more equations, you just keep stacking them. Then you start from the bottom and you substitute up. Again, this has an x, so technically you would first substitute in an x into there and there, but since it won't change anything, I don't write that down, but I will once on part C. You will see that in a moment. So what I now need to do is take this equation and I substitute it in for this x. Question, when I substitute it in, will this x multiply with this? No, when you substitute, what happens to this x? Disappears, it comes out. As Anthony said, it goes to the hospital. So I'm going to replace this x with 2x squared minus 1. And that should be in parentheses if I want to do this, make sure I'm accurate, plus 3. So now let's simplify. Actually, there's not much to simplify there. It should be a pretty easy simplification. I'm not multiplying anything, but I do have a minus 1 and a plus 3. Minus 1 plus 3 is 2. So I'll have 2x squared plus 2 more. There's my answer. You see any all-divisions?
No.
See any square roots? What does that mean about my domain then? Domain is all reals or negative infinity to positive infinity. Yep. Okay, one more, and then you'll see part C. Oh, I want to point out, I just found f of g and g of f, and the equations were the same, the starting equations. Did we get the same answer? No, order matters on compositions. If you change the order, you likely will get a different answer. All right, part C. It says find f of g of 2. So this is where I was talking about you'll sometimes have a number other than x. So I'm going to stack, or let me first mathematically show you what's happening. F of g of 2, it's saying take f and in the place of its domain, replace the domain with the range of g. But actually, instead of replacing with the range of g, replacing it with the range that's produced from the domain value of 2. Now that was a whole mouthful. Yeah, that was a whole mouthful. The easier way to say is stack f on top of g on top of the domain value of 2. So this 2 is in the place of x here. That's a domain value x equals 2.
You would take out the X.
Oh, I'm sorry. Are you correcting me that G's equation is wrong? Is that what you were talking about? Yeah, there we go.
Then when you plug in the X, 5, 2, then plus 2.
That's right. So what I'm doing is I'm going to take this 2 and I'm going to substitute it in for this x. And so what is 2 plus 3? And I guess to be perfectly correct, I'll put it in parentheses, but that parentheses won't do anything. So what is 2 plus 3? 5. Okay, so we now have 5. So let me walk through the, no, I'll do this at the end. So now with my 5, what do you think I do with 5? Substitute in for x. Will this be a 5x there? No, because that x comes out. And so we're left with 2 parentheses 5. That 5 replaces the x squared minus 1. Now let's make sure we follow PEMDAS correctly. Do I multiply by 2 first? Do I square first? Do I subtract 1 first? Square. So what is 5 squared? 25. Okay. Now do I multiply next or do I subtract 1 next? Multiply. 2 times 25 is 50. And then we subtract 1. Whoops. 49. And so we just discovered that f of g of 2 equals 49. Now on this problem, we were given one domain value. What was our one domain value we were given? 2. We found the range to be 49. So let me tell you how this works. We started with the original domain on, let me say G's equation here, and I'm going to do 2 circles, 2 ovals to represent domain and range. Let's say this is domain, this is range. So just put a D and an R if you have circles here. Domain, range. And then next to it, do F with 2 more ovals. And I'm walking you through like this because this is what Alex does on your homework. So this is good just to understand what's it talking about, and then maybe it'll make sense to you. Okay, we started with the value of 2. That was our domain value. What did we plug the 2 into first? Which equation did 2 go into first? G. That means 2 was the domain of G. And it produced an answer for us. When we plugged in 2, we got some range value. What was the range value we got? 5. Okay. Then we took that 5, which was the range of G. So G of 2 was 5. We took that 5 value and we substituted in for X, which means we substituted into the domain of F. So we plugged in 5 there. And when we plugged in 5 there, it connected us to a new range value. What was the range value for the final answer? 49. Okay, so that's the process of f of g right there. That's f of g. You take the domain of g, you start here, that's what went in first, you plug in, plug in, plug in. Okay, so now let me go back and let's complete this slide. This is what kind of homework you're gonna get on Alex, and it's walking through how the domain works. You get the domain of g and it produces some range of g. Well, that range of g needs to exist as the domain of f at the same time, and then that domain will create a final range. So here's it is illustrated. If you had a domain and range of G and a domain and range of F, what you need to look for are the values that connect from the range of G to the domain of F. Which ones would overlap? So like here, which ones would overlap between these 2 circles? 6 does, and what else?
8.
I see 6 and 6 and 8 and 8. So if you were going to come up with your domain and range, you'd find the domain to be anything that produces a 6 or an 8, and the range to be anything that the domain of 6 and 8 produces. So over here, what produced a 6? 2 does. What produced an 8? 3 and 1. So I want to write them in order. So 1, 2, and 3 produce those shared values. So our domain would be 1, 2, and 3. The range your domain is what you start with at the very beginning. That's what you would start with, those values. The range is what you end with, which would be which ones? 13 and 14. Those would be the only things in the range, 13 and 14. Does that make sense to you? Yeah. So that's going to be an Alex question right there. I just basically, I saw it on Alex, I liked it, and I just drew it and put it on your packet for you. So I just want you to know that that's how it'll work on Alex. You just need to make those connections, how they work together. Okay, I walked you through 3 examples. I want you to try to find here. Start with f of g, find f of g, then move on. All right, example 3. So now let me show you how domain can change. So I went ahead and from here on out made it a little easier that I've already stacked these equations for us. We're trying to find f of g. Again, that's just a simple way of saying we want to know f of g of x. You can just composite form write it like that, fog, and that's assumed that that's what you mean. Okay, so I just want to give you that there. So our technique has been stacked. So I already stacked these for us. What we need to do is do what from the stacking? What do you do after you stack them? What have I been doing after? So I already have them stacked up for us. What do we do next? Substitute. We're going to take this one and substitute right there. So this is technically the range of g. The domain is the x. That's the whole equation that generates the y. So that's the range of g going into the domain of f. That's what's happening in as it pertains to those circles I just showed you. So now when we do this, I'm getting the square root of parentheses x minus 1, close parentheses squared, minus 1. As it turns out, you cannot simplify this. You cannot cross out this square root and the square because of the minus 1. They cannot cancel one another. It's not isolated, so you can't cancel it. That's going to be our answer. That is f of g. So f of g of x is going to be what we just got right here. Now, will that have a domain of all reals? No. The domain is not all reals because you can't have a negative square root. So on a view of a number line to kind of show you what the domain would look like, on a parent function of a square root, you can't have negatives, you can't have 0, you can't have positives. So it could be anything from closed circle going to the right, this direction. Now, that's what the parent function of a square root would look like, is that right there. But this is not the parent function and has all this inside. So we're going to take the insides and say that x minus 1 squared minus 1 has to be greater than or equal to 0. That's the first thing we're going to state. Because a square root can be 0, it can be positive, it just cannot be negatives. And now we go to solve. What's our first step of solving this problem or isolating the x? We would add 1. And so I now have x minus 1 squared is greater than or equal to 1. And so now my domain is no longer going to be from 0, it's now from 1. And now how do you get rid of a square? What's the opposite mathematical concept? We square root. Now anytime we add a square root that's not originally there, what comes with that square root? Plus or minus. So we'll have x minus 1. I don't need the parenthesis anymore. X minus 1, there's the plus or minus, is going to be greater than or equal to positive 1. Now if you remember, when you add a negative, that's going to flip your inequality around. So now I have a second answer I need to throw on. I need to have a negative, I don't know where the value is going to be yet. Sorry, take that back. I'm just going to leave it there. No, negative 1. I do know, negative 1. This is a closed dot and it's saying shade to the left. X is less than, so it'll shade to the left. So I now have this added to my domain. I still have one more step. how do I get x isolated if it says x minus 1? We add 1 to both sides, and I'll do that for the other as well. So I have that x is greater than or equal to 2, or x is less than or equal to, what do you get there? 0. So these numbers actually, well, it was -1. Now we'd say it's now 0, and this becomes a 2. That's where my domain would be if I graph this. I'll show you really fast. Again, what I'm going to do here, S equation was the square root of x minus 1. I'm kind of showing you a nice little technique on Desmos here of how to solve this. G's equation is x.
Equal to 2 or negative infinity is less than or equal to 0.
You're close. Okay, here's the picture, and I'm showing you how to type that in as well. Here's the picture. As you can see, this graph is going from negative infinity all the way to 0. Then there's a gap, and then from 2 goes to positive infinity, which is exactly what I had on that number line right there. It's exactly the same thing. So you could write it the way I have it written down here. You could say this is your domain, but it's x is greater than or equal to 2, or it's less than or equal to 0, or you could say from negative infinity to 0, bracket, union, bracket, 2 to infinity, brackets, because it can be equal to those numbers. I'll go one more real quick. We have f of g here. Again, what's our technique after we have them stacked? We substitute. So I'm going to substitute that in right there, and we will get our final solution, that f of g. There's not going to be much we can do on this one either. F of g equals 1 over the square root of x squared minus 1. Can I cancel the square root in that square there? No, why not? Because that has a -1 in there as well. They're not isolated. So there's my solution as far as the equation goes. If for the domain, will it be all reals? No, we know it's not all reals because we're division and we have square root. So let me walk you through one more domain here. We have division. What are you not allowed to divide by? You're not allowed to divide by 0. What about the square root? What are you not allowed to have a square root of? Negatives. So it means it has to be just greater than 0 values. And so we take the algebra that's inside, which is x squared minus 1, and say that it has to be greater than 0. So what's my first step? Add 1. So x squared has to be greater than 1. And how do you get rid of a square? Square root. Anytime you add a square root that's not originally there. So x has to be greater than 1, or x has to be less than -1. We need to add a -1 and say it's less than, so that shades to the left. So this would also have a gap in the middle. So there's my domain. Or you could say from negative infinity to -1, open circle this time, so a parenthesis, union 1 to positive infinity. That would be your domain. You could graph these just like I did. Here's a little trick. If you're graphing them, you would type in the equation. You don't have to graph f, you don't have to graph g, but you type it in just as it's given to you. Like that. And then you would type in f parentheses g parentheses x. If you do that, you'll see the graph. And it is just like we said, it goes forever to the left, forever to the right, but it breaks from -1 to +1. And that's what I was just saying on this slide is you can use your graph to check. So you'll have a DOL, it's your turn to try. All right, now let's look at example 4. And this is where we do the opposite. We're going to decompose. So it says here, find two functions f and g such that h of x equals f of g of x when h of x is given this. Neither function may be the identity function f of x equals x. So we can't have a linear, the basic linear parent function for a linear, but we want to break this apart into two functions. So said another way, normally we stack and we substitute up and we come to our solution. Here's what I'm going to show you, because I'm going to go through, and if you remember your 8 different parent functions, sure, we had f of x equals x, but we also had some other ones just really quickly, just kind of if I were to write them down. The functions that you're kind of thinking about is we could have like f of x equals x squared, f of x equals x cubed, f of x equals 1 over x. These are some of the parent functions that we were given. Let's see, absolute value of x, absolute value of x. These are some of the different parent functions we saw. And so when I look at this one, I can see that I have something here in the denominator. I have this portion of the function. If I pulled this out, I could have my other. So you still might not be following what I'm saying. So let me just write it out and show you. Let's say we needed to find f and g. So where when I substitute g in, I would get f. Well, notice that h of x, if I took this 1 over, and I'm going to use this function right here, so that's 1 over x, what would be left over is the g of x, which would be this x plus 2 squared. So now, if I were to try to substitute this in for x, you'd notice that you would have 1 over x plus 2 quantity squared, exactly what we had. So this would be our two equations here. This would be f of x and g of x. And if you wanted to write it in perfect form, you just throw it in a parenthesis now, f of x and g of x. That would be an option right there. Now, would you have to use this one? No, you can use a lot of different ones, but this would be a very basic one, because I see two different parent functions. I saw a parabola or a quadratic function, I saw the squared, and I saw the reciprocal 1 over x, rational. And so since I saw two different parent functions, I took the inside and the inside. That's inside the reciprocal. So the inside became g of x. And the outside reciprocal, function became f of x. So now that maybe I explained it a little bit better, let's try part B. When you look at part B, at first glance, I see what appears to be quadratic there and linear there, but the problem is you can't break this apart at two different sections. But one thing I can do, I see that a factor of 3 can go all the way across. So what I'm actually going to do is I'm going to change h of x, and I'm going to do a GCF here and pull out the divide by 3 all the way across. So I'd have 3 times x squared minus 12 divided by 3 is 4. That's 4x. And then 12 divided by 12 is another 4. And you could pull from here. And you could say, all right, now I see that parenthesis could be substituting inside. That could be my g of x and 3, and this would make this an x, be an f of x. So you could do it that way and say, well, f of x is 3x, and the g of x that's substituted into the domain of f would be this x squared minus 4x plus 4, and that'd be fine. And I'll also show you, just to make sure we haven't totally forgotten how to x factor. If you x factored this, we learned this the first day of school here. If you x factored this, we find the factors of 4 that add up to be -4. We try to define the two numbers that multiply to be 4, but add to be -4. And the list of possibilities. So it could either be 1 and 4 or 2 times 2. And if I need it to be -4, what it's going to be is the 2 and 2, but both negative. So -2 and -2. Since it's the same number twice, I could say that h of x is 3 times x minus 2 times x minus 2, or just 3 times x minus 2 squared. So if you went like this, you could say the answer is, the answer here would now be f of x equals 3, you could say x squared, and g of x would be x minus 2. Now there's a plethora of different ways you can solve these, but this is an example. This is a one option. I'll say option 1. And here would be a second option. And if you're like, well, is there more? Yeah, you could actually say x minus 2 squared, put the squared over here in the parenthesis over there, g of x, and make this just be 3 of x. So there's a lot of different options, but there I found 2 of them. Now I'll let you try. Given these two, or excuse me, this equation here, try to find two functions, g of x and f of x, that would provide that f of g equals h. All right, now let's look at real world. So computer animation, it says an animator starts with an image of a circle with a radius of 25 pixels. So I have a circle here. Just put this on there, and let's just say this right here has a radius of 25 pixels. Whatever a pixel is, we're saying that's a radius of 25 pixels. So I'll just say r equals 25. And it says the animator then increases the radius by 10 pixels per second. So this radius is actually going to get larger and larger. So my circle, though it starts here, is going to get larger and larger and larger. It's going to increase by 10 pixels per second. It says find, so this is increasing. This is increasing here, 10 per second, 10 pixels per second. So if that's happening, it says find functions, model this data. Well, my first radius is 25. So my R, my original R is 25. Now the next, for the radius, the next radius increases as 10 pixels per second. So what that means is, for my second equation here, I'll just call it R2 for now, or what we can call this G. No, I'll start with R. Now for the increasing radius, I will just go R1 and now R2, the later R, oops, R2. Whatever the value is, it's increasing by 10 per second. Now here's the deal, don't just say 10 like this. This would need to get an, it's going to be increasing 10 per second. So first we would start with wherever we were, which is 25, and then we would need to increase 10 per second. And so if you're using time, let me tell you how people might mess up. It's like this, 10x, because you say, oh, okay, well, I plug in the 10 there. Well, that's not accurate. But we do need to increase 10 per second. So we need to work through how to get the correct answer for this particular problem. And I just paused the video there and I kind of looked over at part B and I realized what I'm doing that's not going to really work out here is they didn't make this clear on the part A. We're going to end up working into the radius or area, sorry. So let me back this up for a second. So we said the radius starts at 25 and then increases 10 per second. So let's just say the radius like this. The radius given any particular time could be found as it starts at 25, but it increases 10 per second. So there's the radius. Okay, so that's where I'm gonna start with my radius. So there's that data. Now, when we go to part B, it says find A of R. Now, what is A? A is what we call the area. So that's the R for the radius. And so the area for the formula for a circle is pi r squared. Okay, that's our formula from way back in algebra and geometry. So what we're going to do here is we're going to try to find A of R of T will equal. And so to find this, what I need to do is really stack. So A would go on top, pi r squared. In the R equation is 25 plus 10t. And so what we're going to do here is I'm going to substitute this in right there into the spot for R. And so this would become pi times 25 plus 10t squared. And I'm just going to leave it like that. So I'll rewrite my answer right here. Pi times 25 plus 10t quantity squared. That would be for every second, that would generate, that for any second amount of seconds, that's how you would generate the area of your circle. So as the time increases, that would be the area of the circle And that's exactly what it represents. So I know you think A is the R. Well, that A is area, but that's just the area formula. So this plugged in, this would be the area of the increasing circle. Area of that of circle per time. For any amount of time, you can find the area of that circle. All right. So it says C, given all this information, how long does it take for the size of the circle to quadruple its original size? So what I need to do is take that original, or that equation that I just wrote down here, that the A of R. And if I want to find its original size, what I would do is I plug in a 0. Let me first just give the equation of T was pi times 25 plus 10t to the power of 2 squared. So if you want to find the original size, so let's first find A of R of 0. So at the original time, you'd have pi times 25 plus 10 times 0 squared, which 10 times 0 goes away. 10 times 0 is 0. So 25 squared is 625. This is 625 pi. And I'm just going to leave it like that. So really, we want to know for it to quadruple in size, we need to know when do we get 625 times 4. So I'm going to go to the calculator here, and I'll type in 625 pi. We need to know when it's multiplied times 4. So roughly 2500 pi, I think is what that is. 2500 pi. Yeah, 2500 pi. We want to know when it's there. And so if you want to know when it's there, I have a calculator for this. It's the InSolve. So I'm going to go to this first link here, InSolve, and it tells me what to do. So that's time 0. So time 0 area equals 625 pi units squared. What we want to know is for A, which would be 2500 pi. So when does this equation, that's really what we're trying to solve. When does 2500 pi equal this equation there? Pi times 25 plus 10t. And we could solve this. You could divide both sides by pi, but I'm going to InSolve at my calculator here just in a second. But here's the algebra as you go through like this. So 2500 we need to equal 25 plus 10t squared. Whoops, squared like that. You take the square root of both sides. We're trying to isolate the t, and so that would cancel out. Now normally we'd say plus or minus. This is real world, so it can't be a negative time. So I'm only going to pay attention to the positive time. The negative won't be real. I'll put the minus here, but this is not real. Not for real world. Not real world. You want to do the negative. And so now I'm doing the square root of 2500, which I think is just 50. We'll check an InSolve in a second. And so 50 would equal 25 plus 10t. I would subtract my 25. You're probably thinking, man, the calculator would have been a lot faster. Yeah, I agree. And dividing by 10, I think the time is going to be 2.5 seconds. T equals 2.5 seconds. Let's see if that's accurate. So on the InSolve calculator, the way to find this is it first says you type in the equation as originally given. So we had 2500 pi equals pi times 25 plus 10, and I need to use an x here to the power of 2. So there's my original. And then it says take y equals the left side of the equation. So y equals 2500 pi, and then take y equals the right side of the equation. The intersection would be the solutions. Now, it doesn't appear. My answers here, it's the x values where they cross. It's going to be 2.5. That's where it's going to be. But it's going to be way up high in this graph. I think it's going to be at 2500 pi, which is like 7,000. So let me just scoop this really quick to like 10,000. 1, 2, 3, and do this to negative 10,000. So you can see there. Okay, there we go. You can see the x-axis values. They come in. These are the two potential answers, but you can't have a negative time, but you can have a positive time. That's the X answer right there. It's where this red line also intersects. So it would be 2.5. So we did it correctly. How about that? Now it's your turn to try this problem here. Come up with your equations. All right, let's look at the ACP question. So the first type of ACP question, what they might do to raise the difficulty is have it where you have a composition of three functions. So here you would just have to stack f on top of g on top of h and then go through the set. So f is x squared plus 2x minus 1, g is 3x, and h is x plus 1. So we would first take this equation h and substitute into the domain of g. When you do this, remember that this x gets removed, so it's 3 times, so this x comes out 3 times, and you would put in here x plus 1. And if I wanted to simplify that, I would get 3x plus 3 when I distribute 3x plus 3. That's by distributing. So now once you have that value, you come back and you would substitute that anywhere you see an x. So in this problem, it actually gets substituted twice. You get substitute right there and right there, which would give us 3x plus 3 squared plus 2 times 3x plus 3 minus 1. And you need to FOIL this out and simplify. So I'm going to have to rewrite this. I'm running out of space. I'm going to rewrite it down here. So it would be 3x plus 3 times 3x plus 3 plus 2 times, I'll simplify this. 2 times 3 is 6x. 2 times 3 is 6. So I think I said 2 times 3. 2 times 3x, 3 times 3. 6x and 6 minus 1. So now I go through simplifying. I'll do a quick FOIL here. 3x times 3x is 9x squared. 3x times 3 is 9x. 3x times, or 3 times 3x is 9x again. And then 3 times 3 is 9 plus 6x. And I'll reduce that to be plus 5. I combine my like terms. I see 9x, another 9x, that's 18x plus 6. Should have 24x. Looks like there's only one solution like that. 24x, that would be 14. So perfect. And now this ACP problem. If you stack them up, we want to find g of f of h. So g goes first. G is 2x squared. F goes second, which is 3x plus 2. H goes third, x minus 2. And we're substituting in with a domain value of -4. So x equals -4. We substitute in. So in for right there. I substitute that in. I should have -4 minus 2. That parenthesis has no effect. So not -4 minus 2 more is a -6. Take -6 and we substitute that in right here. So this time we'd have 3 times -6, which is -18 plus 2. So I'm getting -16 there. You take your -16 and you substitute that in right there. So I think -16 times -16 is 256. Following PIMDAS, we should have 2 times -16 squared. That's 256, I believe. So it'll be 2 times 256, which then would be 512. If I didn't mess up, 5, 1, 2. And so last but not least, could you check this with your calculator? You bet. The best way to do compositions of functions is I have this calculator for this. If you put compositions with Desmos, what you do is you just kind of plug in your equations here. So f is 3x plus 2, 3x plus 2. G is 2x squared, 2x squared. H is x minus 2. It says by default, we're looking for f of g of h. That's not what I want on this problem. I need to switch. I need to do a g of f of h. So I need to change this to g of F of H. And we're looking for -4. So it's 512, just like we got. And if you went down here, you could also just type it in. Again, you need to change this to G of F of H. And yep, it'd be 512. So we did it correctly.